Okay, we are live from YouTube. Okay, so ladies and gentlemen, welcome to our workshop on recent research issues on the sustainability of concrete. Today we have very honorable guests here with us that will share some knowledge and will help us exploring challenging topics in sustainability of concrete. So to our first lecture will be Professor Maruyama from the University of Tokyo. He will give a lecture on the impact of drying on concrete and concrete structures, which we all know it's a complex topic, and he will share some of the insights he has been developing his years of research. Thank you very much. Following, I think we have Professor Shingo Asamoto from Saitama University, who will address climate-induced issues in concrete structures. Needless to say, we know it's a very meaningful problem to our society, and we have to address that in our design and our research in cement-based materials. And lastly, Dr. Yamada will, from the National Institute of Environmental Studies in Japan, he will discuss key issues on the study of alkali-aggregate reaction, which we all know affect the long-term durability of concrete and cement-based structures. And it's also a very complex topic and requires us to have a very careful handling. So we invite the audience that we have here in person and also online in our Zoom meeting and also YouTube to engage with our lectures and ourselves in person here. So we invite you to ask questions and share your perspective in the matters so we can have meaningful discussions. And to finalize, we would like to thank the institutional support of University of Minho, University of Porto as well, and our research institutes and groups, the ISISI and Construct, from Professor Lino Maya. Without further ado, I would like to invite the first lecturer, Professor Maruyama, to come us and join the floor. Okay. Yes, so,
okay, and maybe can I use this one?
Yes, perfect.
Okay. Good. Thank you. Hello, everybody. My name is Ippei Maruyama from the University of Tokyo. And first of all, I would like to express my sincere appreciation for Miguel giving me a chance to talk here, and also Lino and everyone who supports this lecture. Today, I would like to talk something about the drying impact on a concrete and a concrete structure. Of course, people know that the concrete will shrink in the dry environment and the influence on the shrinkage induced cracking. This is quite very obvious and old topic, but I would like to also emphasize that the drying has the other influence on the structural performance. So I also would like to acknowledge my students who worked on this topic. Now, actually, this topic is a kind of my hobby. I do this kind of research for more than 15 years. And also, I would like to acknowledge some of the big national projects which supports this research topic. And first, starting from the natural frequency of the structures. So, for the health monitoring, we generally put the accelerator or velocimeter in important buildings, especially in case of Japan. We have the earthquake frequently. So just after the earthquake, the owner would like to know whether this building can be used further or not. So for this purpose, we put such the monitoring system. And during the earthquake, we can measure the accelerator or the velocimeter or deformation of the structure. And that's by the integral, 2 times the integral of the accelerator, meaning the deformation. And the accelerator multiply the mass of the building, meaning the force input to the building. So therefore, based on one measurement, of course, we should put the several accelerator in the building, but in principle, if we get the information of the acceleration of the building as a response of the earthquake, we can get the stress-strain relationship or the force deformation relationship. And then, of course, in the building, during the earthquake, there are several modes, especially when the building is quite tall. But if we pick up the first mode and calculate the natural frequency, and we can get the information, if we assume that the mass is constant, so we can get the stiffness of the structure. So therefore, I collect the several, the response of the buildings of the concrete structure. And this one is coming from the nuclear power plant. And as you see, that the nuclear power plant is composed of the very thick concrete walls. But even such the members, we see the reduction of the natural frequency, meaning that the stiffness of the building is became lower and lower. And this is the normal reinforced concrete buildings. And then we see the rapid decrease of the stiffness. And some of the structural guys think that the researchers generally think that this is due to the small or middle range, the damage of the buildings. But actually, one of my the colleague found that this damage doesn't happen during the earthquake. It happens between earthquakes to earthquakes. So this is an example of the relationship between the deformation on the force obtained from the accelerator. And we put the accelerator in an important building, and we calculate the every stress force deformation relationship. And we found that every time during the earthquake, before and after, just after the earthquake, we don't have the difference. But from earthquake to earthquake, we see some reduction. So it means that, or it suggests that there is some possibility that something coming from the general environment can reduce thickness of the structure. So, based on this, the data, I think that this could be explained by the just drying of the building, because the drying environment is universal for the reinforced concrete buildings. So, and also, of course, from an engineering point of view, whether this kind of phenomena can be problematic or not, that is a very important question. And when we think about the very tall building, of course, during the design process, we should evaluate the certain range of the stiffness of the structure and also a certain range of the earthquake input. So therefore, we evaluate the structural performance with some range, or not to determine the process. But it seems that the reduction of stiffness is more than what we expected in generally. So I believe that this may have influence on the structural performance against the earthquake. And also, in case of the nuclear power plants, the second mode of vibration is also very important for the supporting system, like cabling or piping. So we put the cables or pipes in a structure, and if with this if the building that doesn't behave what we expected, probably the pipes or cable will be damaged during the earthquake. Therefore, those things could be very important. So I start to start to research on this topic. And first, I would like to introduce the experimental the research on reinforced concrete wall. So I prepared two reinforced concrete walls, shear walls. I don't show the detail. I don't explain the detail of the walls, but this is quite the general code, Japanese code. And the reinforcing ratio is 2.8%. So a very, very high reinforcement ratio. And I tour the specimen for long period because the additional hydration is not desired for this experiment. So I cure the specimen for 90 days. And then I loaded one specimen. And the other specimen is exposed to the drying environment for 1 year because the thickness of the wall is about 10 centimeters or something, 8 centimeters, so easy to dry out. So after reaching the almost equilibrium, I loaded this shear wall. And I also prepared the dummy specimen, something like this, and measure the drying shrinkage of this specimen. So it attained 900 micron, but horizontally and vertically. And then I loaded by using this kind of equipment, and we do the cyclic loading to evaluate the performance of the reinforced concrete shear walls. And I also measure the property of the concrete. So as you see, compressive strength is a little bit increased after the drying. And in case of young modules, it is reduced. And the fracture energy is almost 40% increase after the drying. So we have to think about the impact of these on the structural performance of the reinforced concrete shear walls. And this is what we observed, and after the drying in a shear concrete wall, we found that's a very fine shrinkage in the cracking. So the maximum crack width is just 0.15 millimeter. So it is not visible, and people think that if we look at this, the shear wall, we generally believe that this is quite sound. And then this is our experimental result. So this is the wet sample, and this one is dry sample. And as you see, yeah, maybe I have to use this pointer. Actually, the initial stiffness, so you can see that's the stiffness here, that this stiffness is decreased by 50%. So it is quite large. And ultimate strength is almost comparable here, but the deformation at the ultimate the loading capacity is a little bit increased. So from a structural performance point of view, these two characteristics is very, very important. And now this is a proof that the stiffness of the structure can be reduced just by drying. And the decrease in the stiffness of the wall become 50%. So this is very big impact. The failure mode is quite close, as you see, so very similar shear failure. And I try to calculate some structural things. I briefly would like to introduce what I have done. So based on the rigid body spring network, we try to reproduce the structural performance of this reinforced concrete structure. And cyclic pattern is quite close, and the ultimate strength is almost the same, but the deformation at the loading capacity is a little bit shifted. That was reproduced by the numerical calculation. And this is the comparison of the crack patterns of the experimental results and also the calculation results. And we see that a large number of the fine cracks and the shear cracks as observed in a derived case. And this is not so important. And what is important is how to calculate the ultimate strength of the shear wall affected by the drying. So basically, the ultimate strength can be calculated based on arc-action, and we also have to think about struct width and the concrete strength in the concrete shear wall. And this concrete strength is based on the material property, but also the factors which affect the compressive strength here due to the cracking. I will explain a little bit. So to calculate the struct width, we confirm that the width of the struct in before and after drying is completely same. And if we think about the concrete strength here, we can calculate how much strain observed in this direction, and which has an influence of the concrete strength in this the shear wall. And we calculate this strain is based on a numerical calculation, and then we evaluate the loading capacity. And now the most important message of this calculation that the compressive strength increases by drying has compensates the drying shrinkage induced cracking impact on the compressive strength. So if it shrinks and has a shrinkage induced cracking here, and with less the friction between the small struts has an influence of the compressive strength. But it deteriorates the compressive strength. But also, due to the drying, we see the strength increase, and which compensates that the shrinkage induced cracking impact on the compressive strength in the shear wall. So therefore, if the compressive strength concrete reduced by the drying, it is quite possible that the loading capacity is reduced by just drying. And today I couldn't talk in detail about how the compressive strength is affected by the drying, but if we use the certain kind of the aggregate, especially non-shrinkable aggregate, in this case, we see the reduction of the compressive strength. But if we use the aggregate, which is quite shrinkable, meaning that the aggregate which contains Clay minerals, we see the increase in compressive strength after the drying. So actually, many researchers say that the compressive strength can be reduced by the drying, or some other researchers say that the strength of concrete can be increased by the drying. But actually, this non-consensus state is coming from the type of the aggregate used in a concrete for experiment. And so I think the material property used for concrete is very important. So I would like to talk a bit about this. So now I move to the shrinkage and the shrinkage induced cracks. So now maybe 15 minutes. So in Japan, the natural aggregate resource is now limited. And in the west part of the Japan is suffering from the good quality of the aggregate. And if we use the inappropriate aggregate in concrete, in that case, we see the large amount of shrinkage cracking was found in the buildings and the civil infrastructure. So now, of course, you know, the aggregate types is very important for the concrete quality. And for that purpose, we prepared 3 different concrete whose mixture proportion, volumetric mixture proportion is completely same, but only the Collins aggregate type is changed. And the one is a very shrinkable one. And in this case, we see the large shrinkage like this. And if we use, for example, the pure limestone, sedimental limestone, in this case, we see the very small shrinkage, like 650, 750 micron in this case. So we compared these three concrete under the restraint condition like this. And this is experimental results. So this is quite obvious. If we use the very shrinking concrete, we see the large number of shrinkage in the cracking. And if we reduce the shrinkage by using the non-shrinkable aggregate, we see the reduction of the shrinkage in the cracking. But please think about why this happens. Because if the main resource of the shrinkage is coming from the hardened cement paste, and it is restrained by the outer frame. And if we put the aggregate inside, why this kind of, the different kind of shrinkage in this happens? So that is my question on this topic. And when we swipe the surface of the aggregate by the acetone, we found that if we use very large shrinkage concrete, in this case, we don't see any cracks on the surface. But if we look at the surface of the aggregate using the limestone, we see the very fine cracks on the surface. So it seems that it's a trade-off. So if the total shrinkage of hardened cement paste should be comparable, but due to that, the used aggregate type is different, and one type is large number of the visible cracks, but no fine cracks in this case. But in case of the limestone, visible shrinkage in these cracks is less, but the large number of the fine cracks was observed on the surface. So to confirm why this happens in the case of the different aggregates, we do this kind of experiment. So we cut a small piece of the concrete is restrained by using frame, and by using the digital image correlation, we try to capture how the cracks are developed in the concrete. So actually, I used the impermeable coating on the surface of this side, and I exposed the specimen, the ambient air, this side. So we try to simulate how the surface cracks are developed from outside to inside by using this experiment. And the left side is in case of the limestone, and the right side is the sandstone. So, and this is the minimal principal strain distribution, and this one is the maximum principal strain distribution. And you find that if the shrinkage in these cracks happens on the surface, but it will not develop inside. And in case of the sandstone aggregate, if it develops and this goes inside something like this. So if we close up the picture, I can explain something. So in case of the sandstone aggregates, it seems that the bond between the cement paste and the aggregate is very stiff, so very weak. And in this case, once the cracks happen and leads to the aggregate, and the aggregate is shrinkable, and also the bond is weak. In this case, these cracks penetrate along the ITZ zone. And if it develops further, in this case, the stress here will be reduced due to the crack opening. But in case of the limestone itself is not shrinkable. And also the bond between the aggregate and the paste is strong. In this case, once the crack is developed, but soft in a certain depth, and then due to that the less crack opening, we see the additional cracks here, here, and here. So if the unshrinkable property and the good quality of the ITZ, in this case, the cracks are distributed, something like this. But in case of the shrinkable aggregate and the less bond between the aggregate, we see the cracks developed further, and the visible cracks is made in this case. So actually, the crack aggregate and also ITZ property is very important for the shrinkage-induced cracking. I don't show the detail about which cracks is better, but with regard to the durability, it seems that the large, the localized, the visible crack is not appropriate, and the distributed crack is much better with regard to the permeation or the diffusion of the undesired elements from the outside. So then I move to the stiffness of the concrete. So so generally aggregate doesn't shrink, but there is some range. And if we use the limestone aggregate by using the digital image correlation method, actually cement paste, in case of the water to cement ratio 0.55, which is a general ordinary water to cement ratio, the cement paste shrinkage is something like this. As 60% relative humidity, which is the average relative humidity in Japan, which attains 3,000 micron. But when we use the limestone, the shrinkage is almost zero, meaning that there is a volume mismatch between the aggregate and the cement paste. So we should see the some discrepancy. It produces cracks inside. So therefore, inside of the cracks, so along the around the aggregate, we generally see the shrinkage-induced crack and fine cracks, which can be confirmed by the digital image correlation method. And if we use the limestone, non-shrinkable one, so this kind of cracks distributed like this. But in case of the shrinkable aggregate, the damage is mitigated. It has an influence of the some concrete property. So then I made the 5 different concrete whose volumetric mixture proportion is completely same, but only the force aggregate was changed. And I also made a mortar whose the volume mixture proportion is completely same as that of the mortar part in the concrete. And then I put after the long-term, the curing period, we put the specimen in a different drying condition for long term. And this is the desorption isotherms, water content of the concrete or mortar. And then we measure the Young modulus. I also measure the shrinkage of the concrete and shrinkage of concrete and mortar. So this is the experimental results of the Young modulus of mortar and concrete. I also measure the paste, but I skip today in detail. So, but in case of the mortar, mortar is the one. So we see the decreasing trend, but the difference before and after drying is a little bit smaller than those of the concrete we see. And anyway, we confirm that the stiffness of the concrete can be deteriorated by only a drying process. And even at the 60%, we see the maybe at most 30% reduction of the Young modulus due to the drying. And if we try to evaluate this reduction of the Young modulus, considering the crack opening inside, this can be evaluated by the gap strain between the concrete strain and the mortar strain at the same drying state. So if this difference should be compensated by a crack opening inside. So therefore, assuming that the crack opening can be evaluated by the difference between the strains of concrete and mortar at the same drying condition, and if you plot the Young modulus reduction as a function of the gap strain, we see the relatively nice correlation. So we found that the Young modulus is deteriorated by the crack opening inside of concrete. But then we have to, but how many minutes left? No, it's okay. So we have to control this. So shrinkage reducing agent has been developed in Japan in 1970s. And we are debating the mechanism of this agent. And I would like to explain what is happening in the hardened cement paste. And I also then introduce what happens in concrete. So from a polymechanic point of view, we try to evaluate the role of the shrinkage reducing agent by using the bicol glass. So we change the relative humidity, something like this, and measures the mass change and the shrinkage. And also, we try to put the SRM molecule inside of the bicol glass, and how the behavior is changed was confirmed. And this is experimental results. So the top figures showing the strain, long range change isotherms, and the bottom figures shows sorption isotherms. So this is the bicol glass, and this is the bicol glass plus shrinkage reducing agent. And this is a very famous graph. In desorption branch, we see the capillary shrinkage here. And the general shrinkage is governed by the surface energy concept. And this shrinkage is coming from this desorption branch and the difference from the absorption and the desorption. And this water, additional water, the condensed water makes this additional shrinkage. And if we add the SRA, due to that, the change in surface tension, and also the equilibrium Kelvin radius, we see the reduction of the hysteresis here. And then based on this, the shrinkage is reduced. So this can be, as I mentioned, that this reduction of the additional shrinkage due to the capillary condensation is explained by the change in the equilibrium Kelvin radius and also surface tension change. So combining these two roles, we see the reduction of the shrinkage of the capillary condensation. But when we do this kind of experiment, the picture is completely different. This is a case for the water, the hardened cement paste. And we dry the hardened cement paste in a different RH and measure the shrinkage. And this is the normal one. And this is the cement paste containing an SRA. We see that the shrinkage between 80% and 40% was differed, or incremental shrinkage between 80% to 40% change. But less than the 40%, we don't see any difference between those. And in case of the dehumidifying process and the additional drying process, actually we see some slight difference here, but overall, the incremental shrinkage under the dehumidification process, there is no difference. So meaning that the shrinkage of the hardened cement paste mitigated by a SRA is only acting on a fast desorption branch, and especially on the relative humidity range from 80% to 40%. And what is it? So I try to do some additional experiment, put the specimen in this is a fast desorption branch, and this is water sorption, and this is a strain measurement. And then if we put the dehumidifying process after returning the different points to RH, and we found that from 80% less than 80% to 40% or 50%, we see the irreversible shrinkage. But if we think, if we at the 80%, it is almost reversible here. So less than 80%, we see the irreversible shrinkage, something like this. So it thinks that the SLA acting on the shrinkage mechanism which produces the irreversible shrinkage. So I will not tell you the detail, but this is some CSH agglomeration behavior under the drying happens during the first desorption branch, and the SLA has an influence on this effect, on this behavior. So maybe I will skip this one. And then I investigate the different kind of SRA. So the starting material is water, ethanol, butanol, and the ethylene hexanol. And we try to add a different number of the ethylene oxide on that. And we try to measure how these kind of the elements I believe that they have the different performance on the reduction of shrinkage. So we try to measure. And so this is experimental results of the surface tension of each agent. So of course, water is 72 Newton per meter. And this one is most smallest, the surface tension of the solution. We see that the different level of the reduction of surface tension. But if we try to plot dry shrinkage of hardened cement paste and the surface tension of the porous solution, actually there is no correlation. So this suggests that the reduction of the surface tension of the porous solution is not the dominating factor on the reduction of the shrinkage. This is actually have been discussed for long period, and I confirmed it by experimentally. And I also measure the hysteresis groups of each hardened cement phase, and I summarize the experimental data here. So the green line is a incremental shrinkage from 40 to 10% average, and the red one is 75% to 40% average, and the blue one is the from 100% to 75%. And as you see, the blue line and the green line are almost comparable, but only the orange bars changes a lot. So meaning that still these kind of SLA molecules acting on this average range, the intermediate average range, which is where the CSH agglomeration happens under the first desorption. And we found that these two shrinkage reducing agent shows the almost best performance. And in case of this one, the shrinkage is increased. So, so it seems that the balance of this is the hydrophilic property, and this is hydrophobic property, and the balance of these two are very important. And based on some additional measurement, we confirm that the SLA molecules exist in a gel space. So maybe I need to explain something about the CSH structure. It's coming from the proton NMR reductivity measurement. So we believe that the CSH is composed of the CSH sheet, like a Perelman and Sered model. And in case of the sheets, the distance is very small. In this case, we can define that this space is interlayer water, interlayer space. But if the distance between sheets is large enough, In this case, we can define this space as 0, 4. And it seems that this 0, 4 is reduced under the drawing, and due to that happens during under the first absorption. But if we add SRA and with the hydrophilic and hydrophobic night balance, and with short molecules, in this case, SRA can exist in gel space, and it mitigates some reduction of the space between the sheets, and then the shrinkage reducing performance was attained. So, so a kind of SRA is very effective with the shrinkage of the hardened cement paste. Then again, we try to put the SRA in concrete. And as I introduced the 3 defined shrinkage of concrete with the similar materials prepared. And by adding the SRA, we add the SRA on this concrete, we produce the concrete with the shrinkage. And when we add the SRA on this concrete, we see the shrinkage of this concrete. So these two are the shrinkage are comparable with SR1 to SR1 to PL2 and the SR2 to PL3. And then we see what happens. The result is as we expected. The number of the shrinkage in these cracks are almost comparable to the same shrinkage level of the concrete. This is also. But what I'm very interested in concrete property. So this is a compressive strength development as a function of time. And as you see, when we dry the specimen, exposed to the specimen at the day of the 7 days, we see the reduction of the concrete. But in case of adding the SRA, we see that the no reduction of the compressive strength. So due to that, the damage inside of concrete is mitigated by the reduction of the shrinkage of hardened cement paste. So compressive strength was kept under the drying process. And also, the Young modulus also, we see the reduction when we expose the drying state condition. But if we add SRA, the reduction of Young modulus is very little. So therefore, even though the shrinkage not only the shrinkage induced cracking, but also the concrete property was modified. So a reduction of the damage inside of concrete could be very helpful, especially for the keeping the stiffness of the concrete. Therefore, I believe that for long-term use of building, SRA is quite useful. This is a summary. Thank you for your attention.
So, does anyone has a question would like to ask? Yes, please.
Yes, excuse me, Professor. In one part, you were discussing the difference between the effect of using limestone and sandstone, and you say that, for instance, the bond between limestone and the paste is like a stronger than compared to the sandstone and the paste. I would like to ask, why do you think is that? Why the bond is stronger?
Yeah, in case of the limestone, you know that the carbonates will be precipitated on the surface of the aggregate, like the heavy carbonates or monocarbonates. And also we see, so due to that, there's a possibility that some bonds can be made based on the limestone property. But if we think of the sandstone, the minerals is quartz or feldspar. And in this case, especially the quartz, it is very deep. Sometimes some may say that the CSH can be precipitated on the surface of the quartz, but it seems that the impact is less. And in case of the feldspar, also some may say that the CSH can be precipitated, but based on my experiment, it is less. Generally, we see the water membranes on the surface of the quartz and the feldspar, and the large protonandite crystals was found, and the less bonds was made on the surface of quartz and the feldspar. In case of clay minerals, we see some hydrates on the surface. So I think the mineral property has an influence on the bonds.
More questions?
Yes, please. Question was a really interesting citation, especially about the stiffness related with the shrinkage and the drying shrinkage. And my question is, in your work, did you also study the autogenous shrinkage and the stiffness? Did you find the same correlation? Did you study that? Because what would we find in a high performance, for example, where the autogenous shrinkage is usually higher than the normal stress concrete? What would we expect? Even more influence about the shrinkage or well, because at the end, autogenous shrinkage, it is also due to internal drying, to the reaction of the water. So what would we expect in regard to the stiffness?
If we use the fiber inside, I think the cracks are generally distributed. So the performance is not dramatically deteriorated. But if we think that's the more pure, the concrete type, and especially using the silica film, and if you evaluate the stiffness by using the specimen under the standard curing, in this case, the reaction of silica film is completely different because the silica film is reacted in a high temperature. And if we make maybe the real size concrete, and the inside the temperature attained more than 90 degrees C. And in this case, dramatically increase of the original shrinkage is found. And sometimes it attained 800 microns. And in this case, the real structure stiffness could be underestimated. Or the cylinder specimen, it overestimates the stiffness of the real structure. So I think it depends on how to evaluate the real structure stiffness, but there is a possibility that there is some difference between some concrete specimen and the real size structure. I also have some data on that.
Any more questions? So, like Professor again. So. Now, I'd like to invite Professor Asamoto.
Yes.
What is yours?
Okay, thank you for your introduction and thank you for your joining this workshop. And I appreciate for your organizing everything. Also Miguel. Today, so I'd like to present climate-induced issue in concrete structure. I'm now chair person of ACF, Asian Concrete Federation, a technical committee named Concrete Practice and Feasible Measure for Construction and Design in Hot Weather Conditions based on the material characteristics. Then now I have many colleagues in Asian countries. Then we talking about Asian practical issue. So this is not so much research, but I would like to introduce European research and young researcher situation in Asia. Firstly, this is a photo of in the Sri Lanka. In Sri Lanka, as you know, very hot weather condition, tropical region, South India. And then temperature always over 20 and sometimes daytimes over 30 degrees Celsius. And then researcher and the engineer explained to me, they are very suffering from the plastic shrinkage. In Japan, generally, we don't have so much problem with plastic shrinkage cracking because we can cover the sun radiation and so on. But in the Sri Lanka, sun radiation very strong, and then also temperature is high always. Then they have some problems, and then plastic shrinkage cracking penetrate over members, he told me. And also, this is a slide from the Thailand professor. They also suffering the cracking, especially the slab. And then also this is due to the insufficient curing due to the hot weather condition. Then they also have this kind of cracking in the slab. And then according to him, they are very big slab. So it's very difficult to cure or surface that simultaneously. That is they're suffering this kind of cracking. And also he also introduced some cracking issue in the due to shrinkage, as Dr. Maruyama explained. But the situation in the Thailand and Sri Lanka is anyway, the weather is much different from Japan, especially the hot weather and strong radiation, sun radiation. Then another issue is water. So in the case of Thailand, so there are many heavy raining, sudden raining scope, and also especially the side of the beams, there are some gap and also strong raining leaks here. And then if so, some spalling and corrosion. Corrosion can be induced water penetration and also oxygen. Then that kind of deterioration often found at the side of beams. That is the issue. And then also another issue is from the Vietnam. My colleague explained that they have the big crack in the center of the piers of bridge. Then they're wondering what is the reason. The crack is 3 millimeter, very big. Then that is a big problem. And then, but their conclusion is that this is thermal stress and drying shrinkage. But the question is, can shrinkage cause so large shrinkage cracks, 3 millimeter, and why this is so localized? So, of course, this is also in the Vietnam, there are no earthquake. Then reinforcement amount is different, but they don't know the potential of shrinkage, how much concrete shrink in the Vietnam. And then as Professor Maria pointed out, we don't know what kind of aggregate. We know the aggregate in the Vietnam, but I don't know how much shrinkage can be scattered that depends on the aggregate. That is also a practical issue in the Vietnam, but they don't know. They always say, okay, cracking always caused by shrinkage, drying shrinkage, and improper curing. They don't understand the clear mechanism, the clear reason. They always cracking is always say, okay, this is attributed to shrinkage. But I asked them, how much shrinkage potential in the Vietnam, in the Thailand? They don't know. They don't have database. They always say, I don't have climate room. I don't have this kind of equipment. But I simply asked them, why do you not measure the shrinkage outside? Don't need the climate rooms. Just check the potential. And also they have some cement, a fly ash cement, and they blended cement with limestone powder. And also importance is also the boundary condition. In this case, cracking happened, but this side is cracked, but another side is not cracked. That is not shrinkage cracking, bending cracking, right? And also this one is also interesting. Here is very, very deteriorated corrosion, but here is not totally. Because the reason is here is mainly raining, and the inside no. So that's why boundary condition also, surrounding condition is very important, but they not so much discuss this kind of condition. But another issue is industrial standard and design code. Generally developing countries in Asia have been used mainly American or European Eurocode and ACI, ASTM for material quality. Then, actually in the Thailand and for example in the Sri Lanka, aggregate, also cement property would be different. Also climate is different. So they should have their own code, but not yet discuss this one. That is one motivation to discuss with them. And then another issue is hot weather concreting. Generally in Japan, when we talk about hot weather concreting, the concreting of when temperature is over 25 degrees Celsius. That is actually a little bit special concrete in summer. Here in Portugal, also you have the very winter season, summer season, right? But in the Asian tropical region, always summer season, over not special concrete, not special hot weather concreting. But also they have sometimes applied the empirical model of shrinkage and also other diffusion and summer property based on the another country's code. Especially shrinkage, they use, for example, ACI or FIB code and also JSCE. But that kind of models are based on their country's database, experimental database. But they, in the case of the developing country, they don't have any database, but just fit. Then they talk about, oh, that is not so good, not fit. Of course, it is natural. And then also, they, especially the engineer in the developing country, they always care about the specified value, such as temperature limitation. Okay, how much temperature differential, how much placing temperature. So that is also a big issue for them. No flexibility, always fixed based on the other countries' standard. That is also issue. I would like to introduce one example. For the temperature limitation, allowable concrete temperature in placement is generally less than 35 degrees Celsius. Probably in Portugal is the same, right? But the question is why 35 degrees Celsius? How about 36? 35.5? What happened? What is the issue? Sometimes they engineers are questioned, but they always follow the ACI and specification. But recently, in the case of ACI, ACI did not specify the value. I discussed with some American professor. He told me, oh, that is should be flexible, not so much put the value. So it should be engineer judgment necessary. But for easy way to follow the specified value is easier. If flexibility exists, okay, what is the responsibility? Okay, some problem happens, completely your responsibility. If so, everyone don't want to avoid, right? But if we follow this value, that problem happens. That is not my fault. If so, it's better for practical engineer. That is the issue. Then also another issue. This is a very interesting situation. They try to reduce anyway placing temperature. What they did, like this. But you can see how they always say, okay, the temperature is less than 28, but ice is dropped. Then I'm wondering how they control the unit water contents correctly. And also, ice may remain ice, not dissolve. If so, I don't know, if even the temperature is okay, but what some problem happen later, that is issue. Just focus on temperature. Also, this is explained by the Sri Lankan professor, Professor Nanayakara. Anyway, temperature limit in Sri Lanka is maximum temperature shall not exceed 70. And the maximum temperature differential is within the 20 degrees Celsius. It is coming from BS, British Standard, due to the historical reason in Sri Lanka. And then his question is, if it is exceed, for example, temperature differential exceeds 20, summer cracks surely occur or not. Actually, this is very more safety value. But if they specify it like this, it's very difficult, especially the hot weather condition, especially the maximum temperature temperature can be easily increased over 70. Then they are suffering this point. Then this value is also specified as ACI, and then, but this is also only specified in the ACI 301, but it is not specified in the ACI 307 in the massive concrete committee. That means probably also the American professor said that ACI has some flexibility. 301 is specified, but 207 is not specified. But that kind of background not much understood in the developing country. That is issue. Then generally temperature limitation is based on to avoid based on DF, delayed transient formation. And then French is a very focus into this kind of issue due to the nuclear power plant. Then there are a lot of the experiment based on the French cement, French aggregate. But Japan, we just installed the French recommendation. Then now also we have this kind of temperature limitation now. But in fact, in Japan, there are no clear DF deterioration in the real structure. Experiment may occur, but the real structure not yet. So that's why now practical engineer in Japan is very suffering this kind of regulation. So just install the other guidelines sometimes have problem. Then also practical issue is temperature in hot weather condition. According to the developed countries engineer, they always cast concrete at night, not daytime. The reason is especially morning. The reason is the traffic jam. Thailand, Sri Lanka is so heavy traffic jam, they cannot transport the concrete for less than 2 hours. Problem is very not practical, technical issue. That is a social issue. And also, they always check the limitation using a mock-up test. But mock-up test is not specified. They just make their own sites and check the effect of the temperature. So that is also sometimes not so much clear. And also now in developing countries, as Sri Lanka, Thailand, and India, they always use mineral admixture to reduce the heat. But why should the maximum temperature less than 70 degrees Celsius, even if the replacement ratio of the mineral admixture is higher? This is about over 30% of fly ash replacement. If so, later I will explain, DF can be greatly inhibited, but they just follow the temperature. They don't care the material. That is the issue. Another issue in the concrete property and material limitation in the Asian country, I often heard they suffering the cold joint. Then, according to them, they follow this initial setting time. This is 3.5 MPa resistance, penetrate resistance, according to STM and BS. But Sri Lankan professor asked me, what is the background of this value? Then I checked many literature, and then I only found this paper published in the 1955. Then, but they just say, okay, this vibration limit will be reached resistance of approximately 500 psi. It corresponds to 3.5 MPa. But this is not clear background of experiment. But they just follow. And then 3.5 MPa is very, very stiff. If so, cold joint easily occur. But then in the past, it is specified. But now, recent STM is not specified. So that's why sometimes this value is, they just follow the past value, previous specification, but they don't change mind. That is the issue in the Sri Lanka. Then recently, our study, 1.5 MPa is the threshold to form the cold joint. So that's why they should check that kind of recent work. And also plastic shrinkage cracking assessment. Generally, this ACI has this kind of Marzell formula equation. And then this also equation and also evaporation rate, specified evaporation rate that based on the powers work that 1936, a very old one. So probably they need to also check that this value is very applicable to the their country, and also they also need to check that their material applicability and so on. That is also the issue of such kind of value. And also recently they also discussed map cracking issue. This is Sri Lanka, this is Thailand. If we see that this kind of map cracking from Japan side, probably Dr. Yamada will explain the ASR issues later, but generally we always think that this is ASR. But they always say, no, this is not ASR because we don't have reactive aggregate. We have never experienced. They always insist, we have never ASR. Then probably this is not necessary. And also they that's why they always say, okay, temperature very high, that's why DF. That is just a simple question. They just exclude ASR according to their experience. But the problem is what they judge, reactive or not reactive, just chemical method. And then that is based on the chemical method, but probably you may know this standard was withdrawn to 2016, but they still using. Then probably Dr. Yamada will explain that later, but anyway, problem is they just use this kind of old method. And also now probably Dr. Yamada explained, we have the very state-of-art technology to detect the ASR. Then actually, in the case of Thailand case, ASR was found according to Dr. Yamada's work. Then also recently in Thailand, possibility of ASR is recently studied. Then probably ASR would occur even in India or other countries, Sri Lanka, but they don't check. And also another point is recently they use the fly ash and especially fly ash. If so, both ASR and DF can be inhibited. That's why probably near future may not occur such kind of map cracking, but fly ash property is different in each country. So that should be also studied to check how it can inhibit DF or ASR. Then anyway, based on this kind of experience and discussion with the Asian countries, research and the engineers, now I established a technical committee to deal with concrete practice and feasible measure for the hot weather concreting. Then just some member is here. And then now we are surveying the practical problem in each country due to hot weather condition. But generally, their suffering is cracking, especially the improper curing and so on. But also hot weather condition, we still have some more research. We still need more research. What happened? So for example, 35, 36, 37, 40, what happened in the concrete? And also their material is different. The cement properties, the characteristics are different. If so, probably more research would be necessary. So that is also interesting issue. In Portugal also, your temperature is sometimes over 30, and you said that sometimes 40. So we still not so much clear understand what happens under 40 degrees Celsius and so on. So that is also one motivation to discuss with them. And then also now we try to summarize the technical report to deal with the practical issue in hot weather climate. And then finally, if we publish some guideline to summarize the issue and feasible construction and design in hot weather condition, it is a very good goal, but we still discussing. And then now we try to summarize their issue in the report. Then hopefully it will be opened soon, maybe within this year. And then if you are interested, you can also refer in the ACF, the homepage. Then we summarize each country's, each situation, and what is the problem, and then what is the testing method in each country, and also what is the standard condition for test and curing in each country. So that kind of information will be somehow somewhat useful to the Asian country. So this is a remark. So from my side is that's all. Thank you for your kind attention.
So, do you have any questions, Professor Asamoto?
Yeah.
Thank you for the presentation. It's really interesting, and it's a really complex situation because you have problems in all of the states of the construction and also the definition of the materials. What do you think it will be the most, not the most useful, but the most simple solution for this problem? You think that if you define some guidelines for them to apply, or to define some tasks for them to execute during the process?
Yeah, that is a very difficult question, because especially the construction quality is very dependent on the situation. Then, but also one problem, they don't know what happened. They always say, okay, everything is shrinkage. But can shrinkage occur such a large crack? Can shrinkage cause this crack? It depends on boundary condition. If they know what happened, if so, before the construction, they can design to avoid such kind of cracking. For example, if shrinkage is 1,000 micro, we can do something to avoid the structural way. And also if their reinforcement is inadequate to cause large crack widths, if so, they can put more reinforcement. The problem now, they don't understand the reason. They just say crack. Of course, in Japan also same, but the development company more. They just say, okay, improper. But also another problem of curing. That's why that is a more practical countermeasure. So it should discuss more.
Okay, thank you.
Thank you.
If I can give a suggestion, you can look into the guidelines from Brazil, because we have some of these problems with the hot weather and the humidity. And we also use guidelines that are based in the European and the American, but we're able to develop more and study more into this topic. So the Brazilian standards may have some options.
Yeah. Okay, thank you. Yes. So actually, that's why we also asked them that there's any database of experiment and so on to check the possibility application of our formula and so on. But they said they know. But Thailand, one professor very actively works. They keep collecting the experiment data. So if so, maybe somewhat interesting to have formulated.
Do you have any more questions?
I have two questions. One is about the wind. If you study the wind, because here in Portugal, we know that hot weather is bad.
Yeah.
Wind is bad, but when we have hot temperature and wind, no way, slab will crack if we don't protect. And did you introduce the question of the wind?
Yeah.
Here in Portugal, at least we have wind every day in some place. Sometimes we don't have here, but the wind is there. We never control which the wind will be. And in Sri Lanka, Thailand, the wind was also an excuse, because here it is always an excuse. Oh, it was in July, doesn't matter, it was wind. The crack is due to wind.
Yeah, that's why it's better to do the some experiment vacuum under the high temperature condition, because this one is, of course, there's some this kind of float chart. No, this is not connected.
We can click here. Yes.
Click. Oh,
I think we can click because it's. Oh,
no.
no, sorry.
Click this.
That's it.
Yeah, and this one, yes.
And yes, okay.
Yeah, this kind of chart exists, but I don't know that is also applicable even the 40, 30, because this experiment work is very old. And then also wind speed, it could be changed. So maybe Sri Lanka case, they also try to check the wind effect by their own experiment. Then also, if temperature is high, the crack is appears very quickly, as you mentioned.
Yes.
So that's why, but still not yet formulated by them. So probably more research and so on is necessary. Yeah, wind effect is very.
And the other question is not about this. You mentioned about the following the codes, the responsibility. Okay, how much we should ponder, how much should we be engineers, or how much should we follow the codes? Because
That it depends on owner.
a teacher, what I always say to my students is, we have to follow the codes. If you follow the codes, it's not your fault.
Yeah.
If the building falls down, you kill 1 or 100%. If you follow the codes, okay, the guilt will be the one that did not follow the code. But in fact, as you told, sometimes we should go out of the code because we should take another decisions. That's
Yeah, that is very difficult.
the responsibility when we are out of the codes.
Yeah, in the case of Japan JSC code, we now move to the performance-based design. Performance-based is not so not the specified value and so on, just depend on the decision of the engineer, just follow the basics principle. But then most of value, for example, 35 is not so much, but for the 20 is a very, very conservative to avoid any possibility. So if you feel this one will not so much affect, so you may have some more evidence. For example, in the case of DF, now I try to change our guideline because if we have, mineral admixture, even the experiment, accelerated condition, no expansion. If so, I may say, okay, if we use a fly as 30% displacement, no limit of temperature. Based on that kind of decent work, we can do something to avoid such kind of, limitation value. Personally, I think that's why this one, the student need to study the decent work. Otherwise, so we just follow the past work, 1950 or I don't know. ACI sometimes change, but also they check the history of the design code, maybe. Also, now you developing the FIB code, right? Recently.
Yes.
Thank you.
Okay.
More questions? No. Actually, in the chat, it's just announcements.
Okay.
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 I'd like to thank
you.
Yamamoto again. And I'd like to invite Professor Yamada to join us. Yeah. And if you like to pass, you can use this. Okay. The pointer, yes.
Okay, good afternoon, everyone. I'll talk about alkali-aggregate reaction. My talk is very different from others, but this issue are relating cracks similarly. And First of all, today I'll talk about this alkali-aggregate reaction from the viewpoint of material science. So first topic I want to say is what is alkali-aggregate reaction? And what is alkali-silica reaction? At this moment, every alkali-aggregate reaction is caused by alkali-silica reaction. Alkali-silica reaction is the most basic reaction causing the expansion of aggregate. But the expansion is generated with the confinement alkali-silica gel affected by the nature of aggregate. Then, in my personal opinion, it would be possible to say the damage by alkali-aggregate reaction expansion is caused by SR under the effects of various factors. So alkali-silica reaction is a chemical reaction, but the expansion is different. This is a very important point to understand why some testing methods fail to reproduce the expansion in field or access. So this is the first step. Then, additionally, I want to emphasize one strange thing for material science or chemists. In chemistry, alkali means hydroxide ion. It's not alkali metals. But in daily life, we call alkali is some material. This material is dissolved in water. Then these materials generate alkaline condition. Such materials, so the kind of ash, we call this alkali. This is our daily terminology, but it's not scientific word. So, sodium is alkali metal, not alkali. But as a general term in concrete engineering, we call alkali is the sodium oxide. This makes confusion in many persons. And why we have to study about the alkali-aggregate reaction is, of course, that we want to control the performance of concrete. But what's the required performance concrete? This is a difficult question. And it's much more difficult to connect alkali-aggregate reaction to such performance. No one can do like this at this moment. Then what engineers have done is they are looking for innocuous aggregate or innocuous safe mixture by some method. Yeah, however, if we want to evaluate how safe this concrete regarding to alkali-aggregate reaction, this quantitative estimation is required in some specific structure, like a nuclear facility. They want to know how long this is safe or not. But no one can respond to such requirements at this moment in this field. If so, what we can do? So as a material science, I want to look alkali-aggregate reaction from the most fundamental parts. For majority of engineers, they want to have some more realistic countermeasure for it. Well, of course, in order to evaluate quantitatively, we have to some model. And unfortunately, we don't know the details of the mechanism even now. So there should be some compromised numerical model. Only we can have. In reality, what we specialists are doing, I want to explain. This is one example. I'm a member of RIDE TC 301 ASR, shared by Jason Illiker of Oregon State University. There is a 3 work package. First one is the validation of test methods. They are thinking about alkali leaching from concrete prism test. concrete prism during the accelerated expansion test. And they want to get some good test method that can reproduce the field expansion. Second part is alkali inventory. That's is a little bit difficult, complicated thing. I'll explain later a little bit. And third one is the modeling. Yes, of course, modeling is very important. But this TC seems to focus on new construction and is trying to develop some performance tests, they call, to judge whether some aggregate or mixture is safe for expansion, but without expansion estimation for a long period of time. For second, I want to explain a bit more. In dam concrete, alkali content is very limited. Even in such concrete, expand in long time. So some researcher proposed a hypothesis from some kind of mineral, such kind of feldspar or feldspar soil. Sodium is released from aggregate, and then this sodium can accelerate SR in long time. But for me, it looks like only a hypothesis. There is no direct evidence for me. But a normal engineer has convinced the hypothesis is some kind of theory. Then they are trying to quantify the effect, and they count the dissolved alkali metal amount to the initial alkali content. And they want to specify some alkali threshold value to generate some expansion by some test method. This is some very complicated. Every time I've been shown some difficult data. That's make troubles, I think. Today, I want to show you some very complicated data. Okay, first one, I want to show this picture. Time it right? There are some documents describing the detailed advanced procedures of petrographic diagnosis. If you are a specialist, you can a little bit easily identify the reactive minerals, such as dolomite, chrysoprolite, opal, volcanic glass, cryptocrystalline, or microcrystalline quartz, or calcedony. Of course, these names you are not familiar with it, but this is very fundamental material, mineral, causing alkali sugar reaction. And with the reaction of this silica mineral with alkali hydroxide, not alkali metal, then alkali silica gel is generated. This is very viscous, generated inside of aggregate. And this gel is confined by cement roast. Then expansive pressure is accumulated inside the aggregate. Then beyond some critical value, plaque generated from aggregate. This is a reactive underside. You can see a crack from here to expand to cement paste. あ、見えてない。見えないのか、これだと。じゃあ。From here, crack start. then crack pass through cement paste and extending to non-reactive chlorides. And this is ETS mapping of calcium. Of course, alkali silica gel is the sodium silicate in the original state. So there is no calcium in the plug of in aggregate, no calcium. But passing through the cement paste, you can see some amount of calcium. But there is no calcium again. From this texture, what do you think? What you can imagine? There is some basic knowledge. Silica gel must come from aggregate because there is no source of silica gel. Then pass through. And once silica gel penetrated into cement paste, there's a lot of calcium. Then calcium react with sodium silicate to form CSH. This is the simple issue. But here, why no calcium exists? This suggests the movement of silica gel after cracking is fast enough to pass through without exchange calcium. The exchange of calcium with sodium is a bit slow reaction compared to the movement of silica gel. This is, of course, the estimation, but this kind of estimation is very important for next topic. So there's no need to say about today. Please look at this one. This shows the relationship of ratio of reactive aggregate in concrete and expansion. This is known as the Pessimum phenomenon. This is the Pessimum proportion. This aggregate shows the maximum expansion at 30% of mixture. And the blue line is the case of total alkali is 3 kilo. But if this aggregate is examined as 100%, this aggregate is safe if the alkali content is less than 4 kilograms. But if this aggregate is mixed with some other non-reactive aggregate, such case is very popular in some seaside cities like Tokyo or Hong Kong or Jakarta or many places. They have to import aggregate from somewhere. It's the cheapest way. So in some case, reactive aggregate and non-reactive aggregate is mixed. Then concrete is placed. Of course, non-reactive aggregate is non-reactive by any test method. But this aggregate is examined as 100%. This is innocuous. But by mixing, this makes troubles. There are several specific structures in Tokyo area. Unfortunately, at that time, no one knows what happens by mixing this one. But after a few years, they suffered a serious damage. So pre-stressed gather made some expansion and contact with others and deformed. Then they have to something to recover it. But they cannot disclose. The general constant didn't want to disclose such thing because who was wrong? Everyone kept regulation, but unfortunately, trouble has happened. So, judging from this, considering this phenomena and travel in field, aggregate test is not enough. So we have to think about the mixture test. For that, one problem is the curing of concrete prism in some humid condition. Traditionally, Ryden method or A-steam or Canadian method for accelerating expansion method. Concrete prism is kept in the humid chamber. Some steel container and water is kept beneath of the bottom of the container. Then concrete specimen is placed and the closed chamber is put in some high temperature curing container. But please imagine, concrete prism is removed from chamber to some measurement path. Then hot concrete is moved to some cool place, then return to hot place. What happens? Water accumulated when reheated. Then water dissolves the alkalis, remove alkali from prism. So in order to avoid, we propose one method that's called the alkali wrapping. I added some explanation here, but it was gone somewhere. But anyway, the procedure is like this. We prepared some water holding material. And in this paper, we poured alkaline solution having the same pH with coarse solution. Then with this paper, concrete prism is wrapped like this. By doing, and as the timing of length change measurement, water is consumed by alkoxylic reaction, then reduced amount of water is re-added. So we can prove the sufficient supply of moisture, maximum supply. Even in the humid chamber, water supply is very limited, like this. These are the cases of two kinds of aggregate. So this solid line indicates the mass change by alkali wrapping, but without alkali wrapping, mass change is very limited. So water supply is not insufficient in traditional way. And there's a big difference in expansion behavior like this. With wrapping, much more expansion was observed. So I believe this alkali wrapping is very important for keeping constant alkali amount in concrete prism and supplying water as much as possible. And this procedure is published as Ryden AR13. So now, there is no need to worry about alkali leaching from concrete prism for even long time. Then I talk about the alkali threshold. Please look at this figure. This is a case of sandy cyst. The reactive mineral is cryptocrystalline quartz. This figure shows the temperature dependence of expansion at different ages. So this is very reasonable or simple. At higher temperature, expansion was accelerated, and more longer age, more expansion. This is very usual case. But in another case, this is the case of gel containing chalcedony and microcrystalline core. At 5 weeks, higher temperature shows a higher expansion. But at longer age, lower temperature shows more expansion. This is quite strange. This is another case. My colleague in University carried so many experiments at different temperatures, 60 degree green lines. Alkali content was modified from 2 kilo to 5.5 kilo. At 60, more alkali are resulting more expansion. This is the reason. But at 40, indicated by black lines, no effect of alkali content was detected from 3.0 to 5.5. There is no effect of alkali content. This is very strange. And red line indicates the test result at 20 degrees. Alkali content was modified from 2.5 to 5.5. Interestingly, at lowest temperature with less alkali content, in the first half year, not so significant expansion was observed, but after that, rapid expansion was observed and exceeded other conditions. Low temperature and low alkali content exceed higher temperature and more alkali. This is very strange. And we observe the crack pattern at the same expansion, around 0.1%, but in different temperature. At 20 degrees, you can see this onion skin cracks. And at higher temperature, crack pass through aggregate without onion skin crack. So there's a big difference of cracking pattern. Then think about this again. Crack forms here, from here, to penetrate into other aggregate. But after some time, this crack in cement paste is exchanged with calcium, and this crack must be choked or closed with this chemical reaction. So in this crack, alkali gel can restored again. But the generation of alkali gel is fast enough. It will be difficult to close this crack by chemical reaction. This is a hypothesis, but if think so, at higher temperature or more alkali, too fast reaction of silica result in a continuous movement of alkali gel outside of aggregate without expansion. This is my hypothesis. So it is very difficult to accelerate ASR expansion because alkali-silica reaction we can accelerate. This is chemical reaction. Higher temperature and higher pH, higher reaction speed. It's very reasonable. But expansion, generation of silica gel to combat to expansion, silica gel has to be confined in some places. But the confining mechanism is a reaction with cement paste. So that's the balance. So it is very difficult to accelerate. If so, what we can do? Yes. But anyway, that's the case of temperature. And many people want to know alkali threshold value does not showing which below such value, we will not, we want to expect no expansion will take place. This is the reasonable case. According to this one, below 3.0, no expansion will be expected very even in long time of period. But unfortunately, this is a case of Norwegian myeloid, some deformed rocks. But this is a case of 60 degree, and this is a case of 40 degree. At 40, by past time, time pass for more than 2 years or 3 years, less alkali expanded more. Then, in such case, we cannot determine threshold value. Of course, as I said, many engineers want to find some good method to just can reproduce the expansion in field by some laboratory test. That's a very terrible result. In general, only we can see. There is one possibility. That's alkali leaching. In this case, we expose two size specimen. One is this 40 by 40 by 60 centimeter block, like this. And another is a 10 centimeter cylinder. So expansion was completely different. Less expansion in smaller cylinder. This kind of behavior has been explained by alkali leaching from concrete specimen. We measure the distribution of sodium, and lighter color means higher concentration. As you can see, significant amount of sodium was lost during 3 years. Of course, without alkali metals, in this case, alkali hydroxide concentration decreases. Then alkali silica reaction stopped. And this is very reasonable. We don't see any expansion in small size. So this may be some reason. Concrete prism test for 2 years. During 2 years, from concrete prism without wrapping, significant amount of alkali was lost. They estimated. But reality is a bit different, as explained like this. Mild acceleration results in more expansion in final. So then we need some model. We can get direct correlation between lab test and field expansion. Then we have to some model convert laboratory behavior to field expansion. One model is a very basic model. This was proposed by Iwamoto in 1992, very old model. But the basic concept is very simple. So Iwamoto, Furusawa, Oga is authors propose this model. First is think about the this dissolution speed determined by all the chemical method. Then this generated ASR gel firstly fills some spaces in rock. Then this gel should be converted to some expansion. And this reaction results in the reduction of hydroxide concentration. Of course, this kind of model, we need to fit some parameters. But by fitting some parameters, this model can reproduce the complicated behavior like this. This chart shows this kind of complicated behavior. So at higher temperature, according to alkali concentration, like this. So model will reproduce this behavior. And temperature dependency was complicated. For this, we applied some RNA plot. Then we introduced some temperature dependency, some basic parameters. Then this model was with the optimized parameter. We applied this model to some field exposure block. Then good correlation was obtained because, of course, in this case, temperature variation day to day was considered in the model. Simultaneously, we can calculate the alkali concentration in poor solution. So if the threshold, there should be threshold value for alkali-Silica reaction. According to this value, there is a still higher value than the threshold value, so expansion will continue. And there is another way of modeling. We have this kind of expansion test at different temperature. And this expansion behavior can be reproduced by this kind of equation. By fitting this equation to this test result, we can get some parameters. Then this model was applied to the field expansion result. Then, as you can see, there's a good coincidence. I think, yeah. Today's my talk is concentrated to the difficulty to determine the threshold value. Yeah. Yes. There are some reasons why the laboratory test can reproduce cannot reproduce the field expansion. So this is the main topic of today's my talk. So I prepared some other more comprehensive one, but today that will be enough for you. Many things I explained and you may be confused. But if you have some inspiration from my talk, you can learn about this. Oh, this content is presented as last ICAR conference, International Conference on Alkali-Aggregate Reaction. That was 1 year before in this. There's a keynote speech paper in that proceedings. You can check again if you have interest in this kind of way of thinking of alkali-aggregate reaction. This is very different from others. For me, this is very natural way of thinking of the reaction from the viewpoint of geologists. So thank you very much for your kind attention.
So, do you have any questions for Dr. Yamada? Yes.
First, I would like to go back to the alkali-silica reaction. I used to say usually it is like a thermal pump in the concrete because it will explode and so the talking is a really interesting topic. That's also to me. But the point on the question that I would like to ask you is about the glass.
Yes.
The fly ash is going down in the world because we have to close the coal plants, and some researchers said that glass would replace partial the clinker. You know that glass has problems with alkali-silica reactions. Some research said that okay, if it is powder and the powder there is no problem. What is your experience? What is your idea about the glass replacing cement and all this topic? Okay, how to deal with this, and what is your opinion about the glass and the concrete and the replacing the cement and alkali-silica reaction?
Yes, just depends on the chemical composition of glass. Some soda glass is not good for it because soda glass contains a significant amount of sodium. By exchanging sodium with calcium, that happens in the cement paste, that results in more amount of alkali metals in pore solution. That may accelerate the caustic reaction. But glass is from volcanic glass. You can use. That's a natural pozzolan, kind of. So artificial glass from some bottles, it will be dangerous. But the important point is the pH of pore solution. pH of pore solution can be calculated from the calcium silicon ratio of CSH. This value can be calculated assuming the chemical composition of glass and the reaction degree. We can calculate this value. Then, of course, we have to think about the sodium concentration. It is possible for material science, I think.
But if it is a thin material, really a powder lower than 50 microns, like the size of the cement.
Yes, but please imagine. There is a silica and sodium. If sodium is added into concrete, what happens? More reaction. But if silica is added, silica reduces the calcium silicon ratio. So the both effect simultaneously we have. So which effect is more or less? So that's a balance. So I understand. This is too small. So this powder cannot expand by itself. But this powder can affect the pore solution composition. That's the problem.
Yeah, because I read some studies because when it is really rounded, the material, okay, we won't find the alkali-silica reaction, but I didn't test it.
No.
I just read and I'm wondering about
well,
how much can we deal, how much can we use the glass powder, really thinner, like the size of the cement or even thinner, to replace partial the cement, because the glass is amorphous material. In some way, there will be some kind of reaction with the calcium hydroxide.
Yes.
Like silica fume or like the fly ash. We will have some kind of pozzolanic reaction. But the point is we are putting alkalis inside.
Because they are not so rich in sodium and potassium, alkali metals. That can reduce the alkali-silica reaction by reducing pH.
Okay.
Yes, but usually some transparent glass of bottle, it will be dangerous. But the silica film is okay, volcanic glass is okay, and but silica fume, if silica fume contains 10% of sodium hydroxide, this is not good.
We find sodium in silica fume.
Yes, there is a description in ASTM standard, I think.
To
Do you have any more questions? Like, yes, yes. Could you show me the license for the light might be active from aggregate to. So based on this, the image, before making the graph, before making the solid rock, typically we just store somewhere. It's this region, and it should have some accumulated expansion force.
Yes.
But you say that to get such accumulation of pressure, we need some capsulation based on the CSH. Can we confirm that such CSH capsulation to produce the expansion pressure inside of aggregate based on this image?
No, unfortunately.
No. Yeah. So this is okay. So it means that this is just a message of the silica gel transport.
Yes.
And exchange of the sodium and the calcium in a silica gel. The rate of those two are too much different.
Yeah.
Okay.
I believe there should be some CSH around aggregate, but CSH is very similar to CSH in cement phase.
But if so, we should see some gradient from the outer surface of the aggregate to.
There is a gradient here,
Yes, there is.
but I've never seen.
You have never seen.
So that's another possibility. Gel formed in aggregate, if the gel is viscous, highly viscous enough, it is for this kind of gel, it is be difficult to move in cement paste because the pore structure is so dense. So viscous material can pass through this one. Then expansive pressure is stored. But another question is why higher temperature crack pass through and why at lower temperature onion skin crack is formed. But this difference can be reproduced by some mechanical simulation.
Yeah. So I have done another question about the ASR reaction of is alkali metal ion is just to help to make the dissolution of minerals, or is there any direct reaction?
Of course, hydroxide ion react with silica.
Yes.
But for higher concentration of hydroxide ion, there should be some cation. That is alkali metals.
Yes, alkali, yes. Yeah, but so based on a picture we obtain, so sodium ions can penetrate into concrete aggregate, right? And if it penetrates into aggregate,
yes,
what happens locally? So is it possible to the dissolution process acceleration or just pour? What happens inside?
What happens inside? Aggregate is porous enough for solution. Porous enough for solution can penetrate into aggregate from environment. So that's in the solution, hydroxide ion and the same molar amount of sodium ion is existing. So simultaneously penetrated.
Penetrate.
And to reach reactive silica. Then silica dissolved means SiO-Si bond change to SiOH and SiOH. So the one OH is exchanged by sodium. So SiONA. Such material is formed.
With expansion, with a volume increase.
Yes.
Because of that, we have
This is a bit. If we have a sodium chloride solution and silica in some closed volume, this reaction is volume reducing reaction. But there is a silica, then sodium and water comes through somewhere and no limitation of this movement. Then the volume of silica increases with the expansion. So in closed system, this reaction is volume reducing. But the silica with endless amount of water then expand.
Okay. So there is a possibility that the precursor of the silica gel,
Yes.
which contain the water, can be formed inside of aggregate.
And as I believe, dissolved sodium silicate is monomer or dimer, not so big molecule. That is the alkali gel. So water glass.
More questions?
Too difficult in chemical.
Like speak again.
Thank you very much.
That we finished our workshop. I'd like to thank for the audience in person and online. Thank you. That's it.